Okay, we can begin again. It's 4 o'clock. So, hi everyone, welcome back to COP 3402. Today we'll be going over the basics of processes, what they are, and we'll be going over process management, connecting processes together, different kinds of processes we can run, sending signals to communicate between processes, all that good stuff. So before we start, just want to go over a few things. So the MyFind project has been assigned for, well, it's assigned today actually. So be on the lookout for that. It will be testing everything we learned about syscalls in the previous lecture. It'll be a lot more difficult than the previous assignment, so I recommend starting it right away. Don't wait on beginning that project, it will take some time. And the Hello project is due at our next meeting, so who hasn't finished the Hello project yet? Okay, so that one's pretty simple, not like MyFind. I recommend not delaying, just do it. It's not that hard. You can get full points. It's easy full points. So any questions before I start? Okay, so let's begin by going over the homework. So homework 6, write a snippet of C code that, using a system call as described in class and in the readings, opens a file named hello.c for reading. So let's take a stab at this. I'll just define a main function here. And make a file, I guess, hello.c. All right, so what's this call we're going to use? Open. Okay, so open. How can I get to the man pages for open? What section is it in? 2. So I'll just press 2 and capital K to go here. So we want to open a file called hello.txt for reading, right? Hello.c for reading. All right, so I'm going to open the same file. So the first argument should be the name of the file we're opening. What should the flag be? We have to pass. What is it? Read only? Okay, so how do I spell it? What's another flag that would work in this case? Close. Well, maybe not that close actually. Read what? Read write only? So you're right, except it's not read write only because only doesn't make sense because it's read and write. So yeah. But you're right. We could also use, I think it's 2K. Read write. That also gives you read and write privileges. And it's not only because it's not just one, so you get both. So we'll just do read only though. How can I check for an error? Okay, what should I be checking for? -1. Does anyone know why I place my numbers that I'm checking against on the left-hand side rather than the right-hand side?
Presumably to make it easier to scan.
To what?
If someone's reading the program, presumably it would be easier to read, just an error check?
No, that's not why. So this is a little tip I picked up from my advisor. In C, assignments are expressions, which means you could actually have code like, if I had placed the, well, I guess it doesn't matter here, but if I had an integer int x and I was checking its value, if x is equal to 1, for instance, I could actually miss the equal sign here and that would be valid C code. So this is like a defensive measure. So whenever I'm writing with a code that has a condition and I have a literal value in part of the condition, I always put it on the right-hand side. That way, if I accidentally make a typo like this, it'll be flagged as a compiler error, and I won't have a mistake of accidentally assigning to a value I didn't mean to assign to. Modern compilers will detect that anyway for you, but I don't know, just a tip I thought I'd share. You don't have to use it if you don't want to. Okay, so what would I do in the case of an error? What syscall or library call would I use to emit the error message? Yeah, p error, that's what we've been using. And then we can just exit 1, or I guess in this case we would just return 1. Why does return 1 suffice? Why do we not need to exit with the code 1?
Because you're in main.
Because we're in main, so main's going to return with the exit code anyway. So, yeah. I'm missing the required headers for this. I'll tell you now, I'm not going to require that you use the necessary headers on a test or exam. You don't have to memorize them. But for your homework, you'll of course need to do that, for the projects I should say, because the code won't compile anyway, or if you don't include them. So, okay, so any questions? Okay, so let's go back to the page. What is the full path of this file? The current working directory of the process is /tmp. Yeah.
I just looked through one of the things that says exit 1, but I think Home 70 wanted exit failure. Is there a reason for that difference?
Yeah. Good question. So if I include the standard library here, I will get access to a symbolic constant, a macro called exit failure. You can see my editor lets me autocomplete its name because it finds it in the header. So I can press, should be able to press a button here to go to this file. Oh, here we go. UCF, there we go. And I can actually search in, so I'm pressing, go back here, oops. GF, go to file in Vim, and it goes to the header file. I can press / to search. I can search for exit failure, and right there it's defined to 1. So it's effectively the same thing as returning 1. It just depends on who you ask. Exit failure might be easier to read than 1. Some older programmers prefer 1 because they know the convention that 1 means exit failure. I guess other people prefer the English text, but it's a lot longer, so whatever you prefer. It's to avoid magic numbers, ideally, which is like the notion of having numbers throughout your code that have some special significance, but they're not named in any way. There's no comments, nothing that describes what they do. You always want to avoid magic numbers when programming. That's generally a bad thing, having magic numbers. So you can see exit success is here as well, defined to 0. Okay, so I guess thanks for the question. Gave me an excuse to go off on a small tangent. So number 2. If the current working directory of the process is /tmp, then where will what is the full path to the file hello.c?
/tmp/hello.c.
Yeah, it should just be /tmp/hello.c right here. Oops, there we go. What can you pass to the system call to tell the kernel to create the file if it doesn't already exist? create. So we would pass, how do we pass it?
Pipe.
Okay, so I guess pipe is the name of the symbol, but it's not really a pipe in this case, it's a vertical bar. Yeah. So vertical bar, we'll learn about pipes today. Vertical bar to OR one bit mask with another. So we'd OR the flag O create. What if I wanted to delete the contents of the file? Trunk, right? Yeah. So I guess quick quiz. What if I open this for writing, but I don't specify O create or O trunk? Yes. So if I write some bytes, so if I have some, I guess I can demonstrate this with an example here. If I have some text in this file, hello world, and let's say I wanted to write the string ABC, without O trunk, what that would do is effectively this. That's what how the contents of that text would change. You'd overwrite the first 3 characters without actually truncating the size of the file at all. So you wouldn't erase the file's contents, you'd just start writing from the beginning and overwrite whatever is there. Yeah?
What if you want to append to the file? Is there an O append?
Let's check. I don't know if there's an O append.
Or an equivalent to it?
There is, yeah, cool. You could do that. You could also open the file and then use this operation here, lseek, to navigate to a specific position in the file. So remember, when we open these files, the kernel is saving a file description of the file. We get a file descriptor back, which points to a file description, which is saved internally in the kernel. That file description tells you where the file's current offset is for writing. So if two processes write to the same file, they're modifying the same file descriptor, they're both going to change that offset. So we'll see some implications of that later when we get to fork and exec. Okay, all right, let's go back to here. What might it mean if the error code is eno_ent? No entry. So what does that mean in what's another way of saying that?
Doesn't exist.
It doesn't exist, potentially. So no entry, no directory entry, because remember directories are essentially mappings to files in that directory. We call this a directory entry when it's we have a mapping between a file, inode number, and then a directory name. All right, any questions about homework 6? Yeah.
For function 2, I'm really used to writing main.c. So instead of hello.c, I wrote main.c and that's why I submitted it. Would that be, no?
That's fine, that's fine. Yeah, for the homework, we're just grading your genuine effort to complete the assignment, not the like accuracy. So don't worry if you make a small mistake like that. Yeah.
I just realized I totally didn't consider this. So if you don't include O-chunking, right, does the file size stay the same as what it was before then? Or like,
It does. It does.
So wait, so what if you like write something bigger?
I think the file size would increase. I have to double check that, but I'm pretty sure it would increase. But
so it's like maximum valid size.
yeah.
Or minimum valid? Whatever.
Whatever it currently is. Calls to write will update the file size as appropriate. Okay. Any other questions about homework 6? Okay, so let's close 6. Move on to the next one. I'll leave that here. How can we determine whether two paths refer to the same file? What can we check? Stat. And what do we check? So what output of stat specifically do we check? The inode number, right? What flag to open will create a file if it doesn't exist already? So we just saw this, right? We'll create. What happens if we try to open a file that does not exist? This is a complement to the previous question. Eno_ent. You get that specific error. Truncates a file on opening. We saw this as well. We already saw this as well. What happens if we open a file that already exists for writing without truncating it and then write bytes to it? We just explored that. You'd overwrite the first few bytes, however many you write. Write a syscall, invoke a syscall that opens a file called hello for writing, creating if it doesn't exist, but truncating if it does. Remember to include error checking that exits with exit failure if the file opens. So I guess back to what we had here, we already have this done, basically. Minus these comments here at the bottom. Yeah?
Are we expected to remember all that syntax?
You should remember how to invoke the open syscall. And you should remember, well, okay. Remember it, but keep in mind that for the exam, I'm giving you 8 pages of double-sided notes. So you can just print the man pages, the first page of the man pages for each syscall we reviewed in class, and bring that with you to help you refresh on how to invoke these syscalls. So remember which syscalls are important, remember which ones you've gone over in class, but the specifics you can leave to your notes that you bring with you. Yeah.
At least to this course, is the reason both of these homework assignments revolve around open because that's the most important syscall that we're going to learn?
Yes, and because it also relates to files, which is another thing we've gone over in a whole other lecture. Remember we had the whole file basics lecture. So open is related to file abstraction. So yeah, it's a useful syscall to know. Mm-hmm. Okay, so any questions about homework 7? Okay, so it's 4:15. I think I'll start going over the lecture now. Let me refresh here. Yeah, all right. So today we're going to be going over processes, like I said earlier, what they are, how we can call them, start them, suspend them, resume them, how they can communicate with each other, all that good stuff. So I'll just begin by saying a process is an abstraction. It is a running program. So remember we had talked about abstractions before. Can anyone remind me what an abstraction is based off what we had said before? No? No, in the back. Or, not the front row, second row.
a way of dealing with more complicated things by peeling away parts that we don't necessarily need to interact with at a given time.
Okay, yeah. Do you have an answer as well?
So just automating stuff so you don't have to worry about it unless you know that you want to.
Yeah, so hiding some specifics to deal with the general case. And usually abstractions can be maybe more complex because of that. Sometimes they can be less complex. I don't know. So the idea of a process is an abstraction for a running program. So this is one thing you probably should take away from this class. A process is a running program. Just remember that one definition. It used to be that in previous renditions of this course, we asked that question 4 times across 4 different homework assignments. I've changed that because students hated that. And then when I was taking operating systems, when I was an undergrad, they drilled this definition into us. We would be asked this like every single day of the class until we were all just chanting a process is a running program. So speaking of running programs, like an old problem in computing that we had was the situation here where if we have only one core, one CPU core, so consumer devices today typically have multiple cores. You can probably check how many cores you have on your device pretty easily by just running a command or going to your control panel on Windows. And in the old days, we only had one core and we had many programs trying to run at the same time. So how could we fix this? Are there any ideas that you might have on how we could solve this problem? Yeah.
Threading?
What?
Threading?
Threading, so you're kind of preempting me. Yeah, so that's one idea, multiprocessing, or threading, yeah. Any other ideas? What's a simpler approach? So we have too many processes, not enough cores, so what can we do?
You execute steps only a bit at a time and constantly oscillate between them.
Okay, so again, good. Again, preempting me, getting ahead of ourselves. What's like a really simple approach to fixing this problem? Priority queue, yeah. Okay, it's also a form of scheduling, which I'm trying to avoid saying. Yeah, just buy more cores. So congratulations, you're all like clearly far past this. But the thing I was hoping to get first was like the most obvious answer is we have too many processes, just buy more cores. And in early days of computing, this is what people would do. They would just buy more CPU cores to run more programs in parallel. More advanced techniques at the time involved distributed programming, where you had a network of CPUs all connected over a network. And it was basically like glorified version of buying more cores, but now they're just connected over a network, not on the same machine. And past that, yeah.
Would that be like the cloud?
Yeah, the cloud is a form of distributed programming, you could say. But the bigger idea that you kind of all already thought of, which was probably like pie in the sky back then, but has now been achieved, is time sharing, where the operating system does what's called scheduling, giving a located time to each process to give the illusion of concurrency. So it might look like your internet browser and your compiler and your video game are all running at the same time, but in reality, the CPU, the OS, is only giving priority to a few of those processes to run at once, or only one of those processes to run at once, and goes back and forth between them. Now, if you have multiple cores, maybe they are actually running at the same time, but if you only have one, it's going to be achieved through this notion of time sharing. Yeah.
So does that mean if you have like 2 things open, it's just flipping between it so fast that you can't like...
Yes. Now that's assuming you only have one core. Now most laptops today, consumer laptops, will have multiple cores, which lets them run multiple processes at the same time, actually running at the same time. Yeah. And this was a big deal in the 70s, because can you imagine going to a university like UCF, where we have these like big computers like Eustace that you log onto, but only one person could use it at a time? It just sounds absurd. So it's kind of crazy just having like only one person being able to use these machines, and then over the course of I don't know how long it took for this to be invented, but then suddenly thousands of students could all log in at once and use the same device. That's kind of what enables, I'm willing to wager this goes on Eustace to enable you all to access it at once. I don't think Eustace has thousands of cores for every student. I think there is time sharing involved, giving you all the illusion of being able to simultaneously access Eustace. Now, that all being said, if we're trying to run programs at the same time with this idea of scheduling, we need a way to stop them and start them to achieve the scheduling idea. And the way we do this is by having what's called this process control block. This lets the CPU sort of stop a program in the middle of execution, record its state, and then resume it later. Now, in the kernel, the Linux kernel's implementation, there is no struct called a process control block. So remember, the kernel is implemented in C. It's written in C code. What's actually in the kernel, and this was in the reading. Did anyone do the reading? Or look at the notes for today at all? Okay, a little bit. That's fine, because I'm going to show you one snippet here. One of the links that we have in the reading shows you this page here, which gives you a snippet of the task struct in the kernel, which is the actual implementation of this process control block notion. This is what the kernel uses to start processes, start programs running, and then save their state, and then maybe stop them, suspend them, and resume them later on. And this is just a summary. This isn't the full struct. It's just a snippet of it. The whole struct definition is really hard to read because there's a bunch of preprocessor code and stuff that's not really easy to read inside of it. Okay, so any questions? All right, so we have these processes that we want to start. We want to start running programs. The way they're actually initiated, the way programs are created on Unix machines, is through this idea represented here by cell mitosis. I think it's mitosis, not meiosis. Where we use these two syscalls, two specific syscalls, to create processes. We use the fork syscall to create a duplicate of the parent, and then the exec syscall to replace that parent with a different process. So it's kind of like, cells here, where when you call fork, the child process, the child cell, is an exact copy of the parent. But because we want our programs to be able to do different things from each other, not all do the same thing, we use this exec syscall to replace the currently running process with a different one. So you'll see this common pattern we'll be using throughout this course of fork and then exec. So now your next question might be, so what's maybe one question that comes from this? If all cells or not cells, processes are like cells, and they're made by duplicating each other, what's sort of, I guess, the central question or originating question? Yeah.
What's the first one?
Yeah, what's the first process? If all processes are clones of each other, where's the first one? So this is going to be the init process. And there are different implementations of init that different Linux machines use, or Unix machines use, I should say. The one that used to be kind of widespread was called sysv. But these days, the one that's kind of won out is systemd. This is a relatively younger program for Unix. It came out in 2015, so Red Hat made it. Does anyone know who Red Hat is? Can anyone describe what Red Hat is known for?
Run seeking.
Run seeking? Okay. Not sure I understand. Okay.
I don't want to be political.
Okay. Yeah, so Red Hat, they have like a proprietary distribution of Linux, Red Hat Enterprise Linux. Or I think it's Fedora, maybe, is the name of the distro. But in any case, they're the ones that invented systemd. It's kind of become very popular and widely used amongst different Linux distributions. And it is controversial, so you say you don't want to be political, but systemd is kind of is political because people don't like how it's sort of become so widespread amongst Linux distributions when the whole philosophy of Unix is like specialized individual tools for each job, whereas systemd is sort of like a large, complex piece of software that does a lot of different things. So I don't know, just whether you like it or hate it or don't care, it is like the dominant init process. So to show you this, I can actually look at the man pages for init, and you'll see it actually brings up systemd as an alias for, it actually redirects me directly to, systemd here. Tells you systemd is a system and service manager for Linux operating systems. When run as first process on boot, as PID1, it acts as an init system that brings up and maintains user space services. So we had talked about user space versus kernel space. Can anyone remind me what that difference is? So we'd seen it in a diagram in the previous lecture.
Kernel space has direct hardware access.
Yes, exactly. So when we invoke a syscall, control goes from user space, where we're running, to kernel space for directly interfacing with the hardware via the actual kernel's implementation of syscalls. Okay. So these running processes, I'll point this out here, this last line. Because we start with system D and it sort of all duplicates from there, we get this nice tree structure. And there are ways to actually view this. So the way to view jobs in Bash is to use this PS command, which I believe is short for processes. You can see there's not much output here. It just tells me Bash and PS. The time that this process was started, I think relative to the, or the time it's been running, I'm not actually sure what the time one means. And the PID, so the ID of the process itself, this one's actually more relevant to us in this class. If we want to see all the processes that are currently running, we want to use some flags for PS. So PS AUX, this will print out a lot more. So what PS AUX does, A is for all, U is for user-oriented output, so it changes the formatting of the output. And then X actually shows you processes that are not attached to a kernel, or to the terminal, I should say. Because some processes run in the background, they're not attached to the terminal inputs and outputs. And so the X flag will show you those ones as well. But if I just run PS like this, I only get these two commands right here. Yeah.
This might like sound a bit weird, but is this what's like going on under the hood when you're looking at like a task manager?
Yeah, it is. Yeah. Now task manager is a little bit different because that's Windows. So I don't know if their way of handling running programs is the same thing as Linux, if they have the same exact format, but it probably is similar. Okay, so another set of flags here. So we're going to remove the U flag this time. So it's just AX, all, and then those that are detached. And then let's see here. Yeah, J, it prints output related to the job management, which we'll see what that means in a second. And then F gives you tree-like output. So if I run this, you can actually see we get this like cool tree structure here on the right, showing us how the processes were forked off from each other to create their children. At the very top, if we go back to the top here, you should see at the beginning well, I don't know why it says K thread, but this is system D. You can tell because the PID is 2.
I saw system D again down further.
Where is it? System D?
It was down pretty far.
So does anyone know? I guess we haven't gone over this yet, but I'll just grab for system D. All right, I think there's a way to do it that is cleaner. We can use PS tree. So there's another command of use. It shows you the processes in a tree-like output as well, but it uses Unicode, so it's a bit easier to read. And yeah, system D is up here at the top. So if you want to run this on Eustace, you can run it with this argument here, ps-a, so to view all the ones that are currently running, all the processes. And with the user argument, this will expand to your user ID on Eustace, this environment variable, or just variable, I should say. And now if I run this, you can see it'll print out all the processes that are running underneath my user right now, which there's quite a few because I'm running like my recording software in my browser. So you get all these other ones running here. And this last one that I want to show, the $$ expands to the PID of the currently running process. So if I run this, it will show me all the processes that are forked off of this specific process. You can see it's just my bash shell, and then the command that I just ran, PS tree, is underneath it. So just different ways to view what processes are running. Okay. So any questions before I move on? All right. So now I want to introduce the notion of standard I/O. So when we run some C code and call printf, what's being called is this function here, internal to the standard library. And you don't need to read the whole thing. What's important to note is that it's passing this standard out argument to this vprintf function here as well. And what this is doing is sending printf's output to a file descriptor called standard out. And the convention is that when a program runs, it receives 3 open file descriptors from the shell. And these are going to be standard in at number 0, so that's file descriptor number 0. Standard out is file descriptor number 1, and standard error is file descriptor number 2. Let's see if there's okay. So I guess one question might be, why should we do this? Why should we separate standard out and standard error and make the file descriptors not attached to the programs themselves, but rather something that they inherit from the shell? What's maybe one benefit of decoupling the files we're writing to from the programs in this way?
Security.
Maybe.
Consistency across different systems.
That could also be a good reason, yeah. Portability.
You have a lot of output, it'd be easy to lose the error in the output.
Yeah, that too. So those are good reasons. One other reason that we'll see with this example, I think, is that it gives us some flexibility in where we can send our outputs to. So for instance, if I type in echo hi, this goes to standard out, which is connected to my terminal. So we saw the echo command before, I believe, right? Just prints out whatever argument you give it. Let me open this here on the left so we can go back and forth. Yeah. If I type in cat, this command without an argument, so what does cat do?
It prints the contents of a file.
Prints the contents of a file, right? But if I don't pass an argument to cat, then it actually will read from standard in. Now I can press Control D to send it the end of file signal, or end of file indicator, so that it stops reading input. And it's also writing to standard out. So again, these disconnected streams are what it's writing to. Okay, one more example, then I want to show sort of the reasons why we have these things be disconnected. So what does grep do? Quick refresher.
Was it like Control F?
It's like Control F, yeah. So it just searches for a string. So if I say grep and then hi, hello, you can see it found a match. Hello, world, bye, hello. You can keep finding matches if you don't pass a file to grep. It'll read from standard in. Yeah.
Is there a difference between ending this with Control D instead of Control C?
So there is a slight difference. Control C will send what's called a signal. We're going to go over this later in the lecture. A signal to the process that tells it to stop running. Control D sends it a end of file indicator, which tells it that it no longer needs to read input. So it exits without this signal interrupting it.
Is that the same thing as a string ternary operator?
Ternary operator?
The thing that like arrays in C, you need to see at the end of a string to know that.
The null terminator, you mean?
That's what
It's similar. Yeah, it's very similar. Yeah. Yeah, the end of file indicator is a little funny. It's not really a character. It's not really a signal. I'm not going to get into it. It's like a whole other thing. It's kind of weird. Yeah. Okay, let me see. All right, so we've reviewed all this already. Yeah. So I guess I'll just answer this directly before we move on. The reason why we want to separate standard out and standard error is because it lets us avoid connecting our programs to a specific file stream. So I'm going to give some more examples later, but we can actually redirect where our program's inputs and outputs come to and go from without having to modify our program's code itself. So it gives us more flexibility when writing code and running programs. So far I haven't really done any of that redirection yet, but we'll see that shortly, I think. Okay. So let's see, running programs. Yeah, we've already seen this. You've seen command line arguments, running programs, yeah. I think we've shown this before. You can find out where a program is with which. So which ls. Have you seen the which command before? No? Okay. So Let me see here. All right, I'm going to skip those because I think this is more important. Yeah. So we can actually take advantage of the fact that file descriptors are decoupled from programs to redirect the output of programs as we're running them. So to demonstrate this, if I have a program like echo, or a command that I'm running, like echo, let me fix this here. Okay. And I say echo hello, like I said earlier, ran earlier. I can actually append a character like this greater than sign, to redirect its output to a different file. So I think I might have shown this before, briefly. I could say like out.txt, and then out.txt will have the output of hello. I can also redirect standard in and standard error as well. So to give some examples, if I say ls, let me go back here for a second. I would actually overwrite the out.txt's contents with, oops, sorry, ls, out.txt. You can see that the directories are printed to out.txt. But we can actually do more than just directly write. We can also append. So 2 of these greater than signs lets us append. So you mentioned earlier like the oappend flag, someone had mentioned that. The shell uses that, I think, under the hood to implement this feature where you can actually append to a file. So now if I open this file, you can see that my directory contents are listed here twice. The bin directory is here twice, for instance. Another thing we can do is pass things that are called here documents. So this lets us pass long strings to commands. So for instance here, grep hello. The way you do a here doc, where you use a here doc, is to use these 2 less than signs, followed by some input, which can be multiple lines long. So I'm grepping for hello here. I can say hello world, goodbye, done, and then you end the here doc with EOT again, and then the whole thing gets passed to the program you're running. So this is kind of useful for passing like long strings to programs. And you can even put variables in here as well, shell variables. So I could say $user. I'll pass this all to cat. Oops. You can see it actually expands $user to my username, bpapis. These are all just examples of things you can do with by the virtue of having standard in, standard out, and standard error, not connected to the program itself, but just things that we can manipulate on the command line. So let's see, do we still have that hello.c file here? Yes, we do. So I can say cat hello.c, and I can redirect cat's standard in to hello.c, and now cat will print out the contents of that file. We can grep with grep we can actually read from other files as well. So we can redirect grep standard in to a file, for example, user includes stdio.h. This will search for all the instances of the word define in standard.io.h. A bit smaller. Yeah, and you can combine them too. So in this example, we have both define and define reading in from standard.io.h, and we're also printing the results to grep results.txt. If we cat that out, you can see the results are all going to be stored there. So yeah, they're not connected. Again, you can manipulate all of them. Okay, any questions before I move on to the standard error example? This one's a little more tricky. Okay, so let's say we try to run the cat command and feed it as input a file that does not exist. So no such file.txt. We get an error message saying no such file or directory. And notice that the output has not been redirected to caterror.txt, even though I have this redirection here. That's because the error messages on standard error. So to redirect error messages, we actually use the number, let's see here if I can copy this. We redirect the results to file descriptor 2. So remember I had said earlier, what number is file descriptor 0? What does that correspond to?
Standard in,
Standard in, and then 1 is
standard out.
standard out, and so 2 is standard error. So if I were to run this command, now you can see, oh, oops, maybe that doesn't work. Error.txt. Oh, you know why? This is an issue that, so bash is throwing this error because the file doesn't exist, not cat, so it's not going to standard error. Maybe I can force this in a different way. Okay, this one seems to work. Yeah, okay. So if I were to try and run grep on my root directory, I would get an error because permission is denied because that I don't have sudo superuser privileges to access any files in that directory. And if I were to try and redirect grep's output to a file called grep results.txt, you'll see that it still goes to standard error. So instead, I can redirect the output to file descriptor 2, redirect file descriptors 2 output to grep result, grep error.txt, and then that would actually have the error message stored there. You can see there it actually has the error message stored. Yeah.
So in those first examples, because the operation failed, nothing was written to that text file.
Yeah, so for the cat examples, which I need to fix apparently, you can see it tells you bash is the one that's failing because the file wasn't found. So that's a different kind of error. It's not cat, so cat's standard error did not print anything. The command just didn't even run because that file wasn't found. Yeah.
Short circuit.
Yeah. What? Now I think I know how to fix this, but I'm not going to talk about it because that's a little unrelated. So let's see. All right, so let's go over another example. This is probably an even better example. Yeah?
Can you go over, you said sudo super user or something?
Yeah. So, I mean, I can go over that briefly. So, when you want to access certain directories in your system, so like example, if I wanted to access the root directory, I can't access that because I'm not a super user in my system. I'm a regular user. You can always elevate to be a super user by prefixing your commands with the sudo command. That's going to prompt me for my password. Now, it's not going to show it if I type it in. You can see I can type it in and press enter, and then it actually will work. Now, don't run this on Eustace. Has anyone tried? You know what happens?
Yeah, that would be.
Yeah, it makes you play a video game if you try to run sudo. Yeah,
I got scared.
yeah. So yeah, don't do that. The sysadmins are just will have fun at your expense. So yeah. Okay, I want to maybe drive this point home. Oh my gosh. About how we can redirect to standard error with our own programs as well. So to really show how we don't need to modify our programs on these file streams, these file descriptors, let us avoid modifying our own programs to change where they write to. I'm going to write this program here that just prints to both standard out and standard error. We're just going to use the standard IO functions, the library functions, fprintf to do this. Standard out. Standard error. And yeah, you can use these standard out, standard error names when you're reading and writing to with fprintf. If you were trying to write using file descriptors, we'll go over that later, but there's file descriptors corresponding to these as well. So let's compile our code, hello.c, and then run it. Actually, what I'll do is open this on the right, so you can see the code and then see the output. Now, if I run this, what do you think I'll see in the output? If I just run this program as is, what should I see?
Standard out.
Standard out, and should I see standard error as well? Why not?
Is it wrong?
Because why?
Is nothing broke?
Okay, so I'm glad I'm running this example. So we will see both. Because standard error is its own stream, its own file descriptor. Your program doesn't have to crash for things to be printed to it. You can print to it at will, and programs can print to standard error whenever they want. So now that we've redirected our outputs to standard out and standard error, we can actually manipulate these like we did with other files. So I could say redirect this to out.txt, standard out. So without any number, this is equivalent to 1, which is standard out. And now only standard error gets printed to the console. If I were to switch this out for 2, only standard out gets printed to the console. And now if I cut out out.txt, what do you think I'll see?
Standard.
Yeah, standard error. We can redirect both as well. So I could say error.txt. Let me fix that actually. 1 here, 2 here, and now everything's been redirected. Yeah.
So both standard out and standard error by default print to the terminal?
Yes, by default, they're both attached to the terminal. And the shell opens them on behalf of a process when it starts by default.
So what's the purpose of having both of them if they both print to the terminal?
So we can separate our outputs, our errors from our normal messages. Like if you have log messages to record when something goes wrong, like the classmate described, then you want to maybe print that to a file instead for being able to review it later, rather than have it be on the current terminal, which is like ephemeral. It's short-lived. It'll not last. So. Okay, let me see one more example here. Yeah, this one's kind of cool. So one more thing we can do is on the shell we can actually say, we can reference file descriptors based off their numbers using this special syntax here. So I can actually say with this, redirect standard error to the same file descriptor that file descriptor 1 is pointing to right now. And if I do this, then you'll get no output. And what do you think the output of out.txt will be?
Both.
Yeah, both. Now again, the order is important here. If I were to do this first, and then run this command, what do you think will happen? So we still get standard error to the output. Yeah?
Is that because standard error actually wants to point out to the system, or because when you run it in the beginning, it's, I'm sorry, I can explain this one.
I think I see what you're saying. So it's because when I run this, if I redirect standard error to what standard out is pointing to first, standard out is pointing to the terminal. But now I've redirected standard error to the terminal, and then after I've done that, I've redirected standard out to this file out.txt. But that's not where out.txt or where standard out is pointing to, and I redirected standard error. So that's why the order really matters. Okay, let's see. All right, I think this is a good point. Yeah, so I guess this sort of illustrates it diagrammatically. We've redirected standard error to different files, and standard out can be redirected to out.txt, for instance. And we can move these around as we want using different redirect operators. But I think at this point, what would be best is to just take attendance. So we'll take a break here for like 5 minutes and take attendance. Let me refresh the page. All right, so we're back. Now, I want to continue talking about pipelines. Before I do, I want to emphasize something about the Unix philosophy. So there's these 4 key tenets to the Unix philosophy. The first 2 are the ones that are most cited. The first one is to make each program do one thing well. So the idea is to make programs that are good at very specific things, rather than make programs that are good at many different things, because they end up usually not being good at those many different things. This is again why systemd is so controversial, because it does a lot of different things. And the other idea is to expect the output of every program to become the input to another as yet unknown program. So the idea here is to make your output as direct as possible, I guess austere as possible, as simple. And you kind of see this in the programs we've viewed so far, right? Like ls just shows you the current files in your directory. Let's see another one, word count. We haven't really seen this one yet, but word count just prints out the number of lines, words, and bytes in a file. So very, very direct. And then grep as well just prints out matches. It'll only prints out the matching words in a file, matching lines. Yeah?
Words as in words, or like what assembly thinks a word is?
Contiguous sequences of characters, separated by spaces. I think that's what word count defines it as. You can see here. Yeah, I think somewhere in the documentation it'll tell you what words are. I think, yeah, right here, right here. A word is a non-zero length sequence of printable characters delimited by white space. So these programs all kind of adhere to the Unix philosophy. And the idea of pipelines is that the reason why they do this is because it lets us connect programs together to form so-called pipelines to easily pass their inputs and outputs to each other to make more complex programs from simpler ones. So, for instance, let me take an example here. I can run the find program to list all the contents in a given directory. So I could actually say find, let's say, let me go to the desktop actually. Or maybe I could go to my user include directory, that's something good. Make this smaller. Okay, so I can pass a directory here. I'll pass my user include directory to find. And what find will do is recursively search throughout that entire directory tree for files. So this is different from ls. ls just prints the current contents of your directory. Find recursively searches the entire directory hierarchy. Now, let's say I wanted to search this output for specific kinds of files. Maybe I want to search for any file that has py, capital P, capital Y. These are probably Python-related files, like Python bindings, in the name. The way I can do this is to use grep, and to use what's called a pipe to pass the output of find to another file, to another command, I should say. So with this pipe here, I can actually pass the output of find to grep, and I want to grep for the string py, and now it actually finds all the matches right away in the output of find. So pipelines are very powerful tools. So I'll do that again. Running find, you get all the files in user include. That's what this does. And then I can pass this to grep to just search for the exact files that I want to find. What's another way to do this? If I didn't want to use a pipe, what's another way to accomplish this goal?
What do you work with type?
If I didn't want to use a pipe.
You could use type.
Type?
Find a Python type file.
No. What's another way to connect these two processes out, inputs and outputs to each other without a pipe? Yeah.
If redirect the output into a file and then use grep on that file?
Yes, I could redirect the output to a file and then call grep on that file instead. Same thing. But pipes let us skip that intermediate file. Instead, the pipe is really, it's kind of a virtual file is how you can think of it. It's not really a file, it's two virtual files because you're reading from one end, writing from another. And to demonstrate this, sort of illustrate it, I suppose. Have this diagram here, kind of shows what's going on. Normally, standard in is attached to the terminal, and standard out is going to be attached to the terminal as well. Terminal output, I'll just draw a line here. And find doesn't really read from the terminal, so I guess this is sort of irrelevant. But with a pipe, what we're doing, when we create that little vertical bar, we redirect the output of one command to the read end of a pipe. So this is going to be the read end of the pipe. I'm sorry, the right end of the pipe, because we're writing to this end of the pipe. And then we redirect the standard input of grep hello to read from the read end of the pipe. And this command standard out is going to be the same thing here. And we didn't use grep hello, we said grep py. I'll fix that. I know it might seem like intuitively obvious, but that's kind of hopefully the point. So a common analogy is like plumbing, like you're having like a stream of water connected to pipes that kind of pervades the Linux kernel in some ways. We'll see another plumbing example shortly with pipes. Yeah?
Is there any other commands that you can use pipe with aside from grep?
Yeah, you can use any command with pipe essentially. So anything that writes to standard out, you can redirect its output to the right end of a pipe, and then redirect another command's input to the read end of that pipe.
So it doesn't have to be find or grep, it can just be pipe.
Yes.
Is a way for you to kind of combine the two.
Yes, exactly. This is just an illustrative example, concrete example, rather than abstract. Yeah, just to show us how we can actually use these commands together. And what's cool is we can keep going. So I showed that word count, the WC command earlier. We can actually add another pipe here and read past the outputs of grep py here to the word count command as well to get the number of bytes, or no, lines, words, and bytes in this output. So I recommend practicing using these pipes because in the next set of lectures, we're going to be seeing how we can actually achieve this functionality in our own C code. There is a syscall underlying this pipe. Like a lot of the things we've seen in this class, there's an underlying syscall that these shell commands correspond to. There is an underlying syscall called pipe that creates pipes, and we'll be using that to redirect inputs and outputs of our programs that we write. Okay, let me see. I think I went over a few things here, so I'll skip ahead a little bit. Yeah. So here's a cool one. Another command that I think is worth showing is xargs. So xargs actually lets you convert each line of an input to a form that is appropriate to be the input to another program. So for instance, what does a file command do? Does anyone remember what the file command does? We had seen this a few lectures ago. Yeah. Oh, you have your hand raised. Yeah, you?
Prints details about a file, such as like they created a.
That's stat. So let me go back to the desktop here. Let me move this directory. Let's see. Okay, so file will print out the type of a file, like its contents and whatnot. If I run ls, I can get all the files in my current directory, and I can try and pass these directly to file, but you'll see I get an error message. Because file expects a single file name as its input, and ls's output is just a bunch of files on separately. If I did find, actually, it might be better. I don't know why I have a .good directory. Let me delete that. So find, yeah, these three files. Pass it to file, it doesn't work. Now with the xargs command, I can actually convert each of these lines to the first argument of a command. So instead, now it actually will print out the output of find for each of these files. So this is like this is a binary, so it's a whole bunch of stuff. It is cleaner if I just run this without the a.out file. You can see it actually just prints the contents of each file one by one. So xargs is also often like useful for converting standard in to command line arguments instead. And one more example here. Something really cool we can do. So here what we're going to do, we have multiple pipes, so we're connecting the inputs and outputs of multiple programs together. We're calling find on user include to get all the files in user include. We're going to search for any file that ends with a dot. So this backslash dot means the literal period characters that we're searching for, and then the character H, followed by the end of the line. So the $sign is a special character. It means the end of the line in a pattern. And then we're going to pass this to xargs and pass that to the head command. So head prints the first n lines of a file. Here we're printing the first 3 lines of a file. So what do we think this pipeline will do when we run it? Can anyone guess?
It's going to do the first 3 header files it finds.
Close, close. So xargs converts standard into the arguments for our program. So this would actually print the first, oh, do you have a guess? Okay. So it'll print the first 3 lines of every file that it finds. And what's cool about head is that it actually also shows you the name of the file when you have multiple. You can see all these different files here. The first 3 lines of code. And this is because, again, xargs converts standard out of the previous command to command line arguments that can be passed to that command right away. So all these files are going to be passed to head, so it'll actually print the first 3 lines of all the header files that are found in user include. And this is just to show, you don't need to know exactly how each of these commands work. Well, you should know how find works and grep works. xargs, you don't need to know too much. This is just to show that you can build complex pipelines from very simple parts. You can kind of just fuse them together, or duct tape them together, if you will. And there are research applications for this. So like I use pipelines all the time when I'm writing code for research or other purposes. They're just very useful. So this is some code that Dr. Gazzola has used for, yeah, what it says here, getting configuration options defined by the Linux build system. So one last thing we can use with pipes is redirect both standard out and standard error. So again, if I try to run grep define in my root directory, I get a permission error, permission denied. If I were to try and redirect this to grep for the word permission, it actually wouldn't find any matches. It's just going to standard out because this message is going to standard error, not standard out. So the way to send both standard out and standard error through the pipe is to append an ampersand to the end of the pipe character. And that would actually send both of it to the second command, and then grep actually succeeds in finding that string permission. Okay, any questions? All right.
Can you use just the ampersand if you wanted just standard error?
So, good question. No, that does something different. And I think we'll be talking about that later in this lecture. If not, I think we're going to talk about this later in this lecture, what the ampersand does. You typically wouldn't use it to write 2 programs side by side. You probably want to use it just to run 1 program, and you put it at the end of running that program. We'll see very shortly what that does. Okay, so any other questions? All right, so the next topic I want to touch on is job management, so managing multiple processes from the shell. So in Linux and Unix like parlance, a job is a pipeline. So it's not just one single process that's running. A job is a pipeline. So for instance, this would be one job. The whole pipeline is one job here. Or what we had before, this is one job, the whole pipeline. So I think, let me show some examples. Somebody had asked before what Control-C does. So if I were to run find in my user directory, you'll see it runs for a long time. You probably have already done this before, but you can press Control-C to cancel that process while it's running. Now, the way this works under the hood is that we're sending a signal called the sig-int signal to this process to cancel it. And a signal is just a way of communicating between processes, just a form of inter-process communication. You can find out more about signals by going to manual page 7 or section 7 of the manuals for signal. And if we scroll down, maybe zoom in a bit more and run this again so it's a bit easier to read. Here we go. There's a page here of all the different signals that are present in the Linux kernel. And they all do different things. You can send them to different processes. Some of the signals that are important here are going to be sig stop. So how can we can actually send that signal as well from the command line. So if I were to say find and then slash, if I press Control Z, that sends the stop signal to the job. So it's suspended. I don't really like the word stop because it makes it think like it kind of sounds like it's done running, but it's not done. It's just suspended, really. And I can resume the job later by typing in FG, which lets me send it to the foreground, reattach it to my terminal in the foreground, so it continues running right here. Yeah?
What we're talking about with the CPU handles multiple things. When you stop it, does that mean the CPU actually has paused it, or just that the interval at which it's spinning it is changed?
It's actually paused it, so it's not running that, well, it suspended it, so it's going to be giving CPU time to other jobs instead, And the kernel is only able to do this because it has these task structs recording each struct in memory, or each process in memory, what it's doing. So I'm going to cancel this since it's taking a long time. Okay. Yeah, and FG is a shell built in, so what should we use to get help for it? Should we use man?
Help.
Use help, right? Yeah. All right. Let's see if there's anything commands here on background. Okay. So we brought that command back to the foreground, but you can also send commands to the background. And I guess what's worth highlighting here is that background commands are not interactive. You cannot interact with them while they're running in the background. You cannot send input to them from the terminal. And they're not, but they will perhaps still send output to the terminal. So for instance, if I were to run this find command again, I could press Control Z to suspend it, stop it. And then if I enter, instead of FG, BG, this will send it to the background. Now it's running as before, but if I press Control C, because my terminal is no longer connected to this command because it's in the background, the signal is not being sent. It's being sent, but it's not being sent or received by, I should say, by the find command because it's running in the background. But it's still attached, still printing to my terminal. Its standard out was not changed, so it's still printing to my terminal window. So I think, yeah, I can't send it to the background either because Control Z doesn't work either. So I'm going to have to get a little bit ahead here. There is a way to save my window on the left here. I'm going to have to use a command called jobs. Actually, not jobs, sorry. I should probably use PS. This is a different window, so it would be a different one. So I'll say PS, let's say -A, and I'm going to grep for find. We can see there is a find command running on my machine, only one find command. What I can do is copy this PID and then use the kill command to kill a specific process that's running. And if I run this, you can see it actually stopped here on the left. Let me go back here and see if there's more. Yeah, okay. All right, so any questions about what we just did? I'll go over it again, but yeah.
Is that kind of runaway car thing what's supposed to happen when you use the BG command, or is that just an example?
It does. It will happen in that case. It was supposed to happen in that case because it's disconnected now from the terminal. So for the input at least, so I can't send it a signal with the key bindings, Control C or Control Z. So I'd have to kill the process with a separate command.
But like usually backgrounding stuff and then fetching it is something your CPU is just going to do for you.
Well, if you put something in the background, you do it with the presumption that you're not trying to interact with it. If you wanted to interact with it, you wouldn't put it in the background. You put it in the foreground.
So it can't be retrieved.
There is a way, I think, to retrieve it. It would be, I'm not going to show it, but there's some commands you could run to put it back to the foreground. Yeah, you could. Yeah.
When you resumed the process, did you just use Control Z again? Or did you use a different command?
To put it in the background or?
When you paused it
Okay.
and then resumed it. I mean.
So Control Z will suspend it. To resume it, you press FG.
Ah,
FG goes back to the foreground.
alright.
So there's a distinction here. You can resume it in the foreground and resume it in the background. In the foreground, you can interact with it. You can send it signals. You can send its input from the terminal to its standard in. In the background, you can't do that. You can't send stuff to standard in. You can't, if you send signals via the command line, like by pressing key sequences, key bindings, it's not going to work. You'll have to send a signal via the kill command. So again, I can do this here. I can run it again. Control Z, and then BG. Now it's in the background. And now if I say PS-A and grep4 find, I'll find that PID. Then I can use the kill command to kill that process with that specific PID. And now it'll stop.
Also, so what is the practical use of making some process into the background beyond, I guess, trying to run a bash script and you don't want the user pressing stuff?
If you want to do multiple things at once, so you might want to use that terminal window still, but you don't want to have to interact with it. You want to be able to run it while running some other program. So another application that I can show you, putting something in the background, or suspending a program, would be, this is slightly different, but it's similar. I could say test.c, open this up, have some code here that I was just messing around with. I could press Control Z to suspend this process. I could do some other things. Maybe I could compile my C code here. And then FG to reopen it, and my cursor is still where it was when I exited out of Vim. So my cursor doesn't go all the way back to the top. I don't have to find my place. If I'm in a big file, that's going to be a big deal because I don't have to go all the way back down to where I was previously. So it's like a way to have a quick and dirty like development workflow. That's one application of it. Yeah. I think I have some jobs running right now. No, I don't. Okay. All right. So another one that's cool that I think one of your classmates here has presented to me. The question about what does this ampersand operator do by itself. If I were to run find with the ampersand at the end, it immediately will go to the background. So now Control Z, Control C, they don't work. So I have to do this whole process again of searching for the process and killing it. But actually what I can do, I'll show you another command, is use pkill. So pkill will actually let you type in the name of a command, and it will find all running programs whose names match the string you pass and kill them all. Well, send them all the terminate signal. So if I run this, it will immediately terminate the find program for me without me having to find the whole PID. All right, this one's, now I'm going to show this. So if I run this command, this is going to run 3 commands. The first one is sleep, and it's going to sleep for 1 minute. Sleep, all sleep does is it just suspends execution. So maybe I should demonstrate this in a smaller example. Sleep for 1 second here. My terminal stops for 1 second. I could say 5 seconds, and it just stops for 1 second, for 5 seconds. If I run cat with the ampersand attached, it will be stopped because cat can't actually, well, cat's not actually running in the background because cat reads from standard in, and because it's attached from the terminal now, because it's in the background, it's not actually going to be running at all. And I can run grep hello, and grep without any arguments also reads from standard in, so it has no, it's also going to be stopped because it's waiting for some input, but it can't get any because it's in the background. I can use the jobs command to view what commands are currently stopped. So to view all my current jobs, I should say, which ones are stopped. So I'd recommend knowing like just how to view jobs. You can use the jobs command for that. And then I can use FG to specify which command I want to bring back to the foreground. So if I want to bring grep back to the foreground, I can actually say FG2, and I can type in, you know, hello, hi, bye, hello, Control D to end it, and then that would work. Yeah.
For purposes of this syntax, jobs is commands you've input into terminal?
A job is a pipeline of commands. Yeah, so a pipeline is a job. So if you have multiple pipes connecting multiple commands, that's one job. Mm-hmm.
So one line break, or one character?
You can think of it that way. Yeah, you can think of it that way. Yeah.
Would pkill kill commands that are, or processes that are paused?
I think it would. Let's check. So we can actually check right now. So if I can type, okay. Jobs, pkill cat, operation not permitted. Probably because it's stopped. Maybe because it's in the background, or probably not because it's in the background. Because we were able to kill that find command earlier and it was in the background. So I think it's because it's stopped that it's not permitted. I'm not sure why, but yeah. Actually, this might be the reason why. Let's see if this works. So far we've been using kill just as is to end processes, but kill doesn't actually kill processes. It's kind of misnamed. What kill actually does is it just sends a signal to a process. And it just happens that the signal that it sends by default is sig term, which is a signal that is one of the signals that signify that a process should terminate. There are multiple signals that mean that a process should terminate. I believe it's all of these ones. All the ones in this first group here are signals that mean that the process should, well no, this one, sig term, sig emt, sig hup. All right, well okay, I can't remember which ones are the ones that mean the process should terminate. There was a grouping here that I saw somewhere that tells you it. Anyway, by default, the kill command only sends sig term, which is right here, number 15. This is the actual number of the signal. And the problem with that is that the terminate signal politely asks a program to shut down, and programs can override those signals, and they can have their own handlers for handling them and changing how they respond to those signals. So a program might not terminate right away if you send it the sig term signal with just a plain call to kill. The one signal, one of the two signals that cannot be overridden, is the sig kill signal. This is number 9. So if you really want to end a process, you send it the sig kill signal. So for instance, right here, I'll run sleep for 1 minute in the background. This has process ID 85190. I can run kill with -9 to specify that I want to use the signal number 9, which is the kill signal, to really kill the process without activating any termination handlers. And then that would actually kill the process. And you can see it says killed here instead of terminated. I wonder if this would work for cat. And it did work. So yeah, that's why it didn't work earlier with kill. Yeah?
So, I was gonna see if it's something related to it, but let's say like whenever you're on your Googles or any kind of applications and it's running and it just like crashes and you can't do anything about it. When you go to your task manager to like force quit it, is it the same thing where you're?
So again, that's Windows, so it may not be quite the same thing. But in Linux, it would be effectively that because there are like task manager equivalents in Linux. It would effectively doing this, sending the kill signal. Yeah.
Can you PKL system D?
So I'm not going to try that. There might be a way to do this. There might be a flag that prevents you from doing that. Yeah, I don't know. I'm not sure if I want to try that. You can try it and let me know what happens. I know that for RM, so you might have a similar question is, can you run this command? RM root. I'm tempted to say enter just to show you that it'll say no because it's not an empty directory, but I'm not going to do that.
Let's do it useless instead.
You what?
Let's do it useless instead.
Yeah, let's do it on useless instead. Yeah, no. But RM actually has a special case here where it will not delete root unless you specify no preserve root. I don't know if init has a similar thing, no preserve init, or not init, kill, no preserve init. I don't know if it has that, but yeah, good question. Yeah, and so likewise, how we could run find, and I can press Control-C to cancel it. Some programs might specially handle the interrupt signal, sigint, as well. So again, kill-9 is going to be your surefire way to actually stop a program, kill a program. Okay, any questions about signals? Yeah?
Can a program refuse a signal?
Well, it can set up a signal handler that does nothing for the signal. Yeah.
Is that like, so like hypothetically, like if you tried to send multiple kill signals to a malicious program, it could just have a
So
built-in case to refuse it?
That's a special case. It can't, because again, right here. Where can I find it? Somewhere in here there was. The kill signal cannot be overridden, essentially. That's one of the two signals that cannot be overridden. I'm trying to find the part of the manual here that right here. The signals sig kill and sig stop cannot be caught, blocked, or ignored. So this is to give you like, final say in what programs can run. Yeah.
Yeah, but what if the UUID is like rotating? How would you catch that one?
How often is it rotating?
Every half millisecond, like a root kill.
You could, I mean, pkill is going to identify it by the name. So I don't know about how long the latency is going to be between finding the name and the PID. But I assume if the PID is rotating, it must be forking. There must be a parent that's forking and execing and creating children. So you probably want to kill the parent process, I would imagine. I don't know. I haven't really seen that issue, but yeah, it's a good question. Granted, this all assumes you're like manually killing processes. So there are ways, again, to send signals and interact with signals from within C code. We're not going to be looking at signals so much in this course. We're going to be focusing on pipes as the main form of inter-process communication. But just know that there's really two main ways for processes to communicate, pipes and signals, and we're just going to be focusing on pipes in our C code. But signals are another way that you can use to communicate between processes. Okay, I think I just showed this development workflow where you use vim and then Control-Z, FG, etc. Another way to have a better development workflow is to use what's called a terminal multiplexer. So an example of this, there's one that we have on Eustace called, I think it's on Eustace, called Biobu. I'll see if I can log in here. Yeah. So this is a terminal multiplexer. It lets you create different, basically it's almost like things you can get with a web browser you have in a terminal. You can have multiple tabs, you can have split screens. Let me see if I can view the commands here. Yeah, so you'll see you're in Biobu because the status command is down here. Status line is down here. So F2 creates a new window. I don't really use Biobu often. I use another one called Tmux. You can see I'm getting new tabs opened up at the bottom. I can close one of them, or two of them, or three of them, and the other ones still stay as they are. Yeah, what's cool here, so if I echo command like echo hello world, I can press F6 to detach from this session. Then I can go back to my desktop. I can then log back into Eustace, run Biobu again, And okay, well, it doesn't work. But normally what's supposed to happen is you would see the same text that I printed to the console still there. So I've actually used VOBOO before on other private servers we have at UCF to start experiments that take like more than a week to complete. And I can start it, press F6 to detach, I can exit the shell, the terminal, and then I can just come back on, log back on like a day later or 2 days later or whatever, and then go back into VOBOO and see how my process is going, if it's still running. So that's one more reason. Somebody had asked, like, what's the practical application of running a command in the background? That's another application. Yeah?
The 8x, that's telling you how many and at what clock the virtualization is giving you?
That are available, yeah. I think UCS has more than just 8 cores, I don't know.
Oh yeah, I mean, well,
But
this is probably specific to your session, right? Like it's
Yeah.
giving you this many cores at this speed?
yeah, I think so. I mean, I'm not sure. I'm not really an expert in VOBOO, but I would guess. Okay, so I'll just exit this. Okay, so I'm not going to use VOBOO. I want to show you some examples with the one that I use called tmux, which I don't really use much anymore nowadays. I have another way of achieving what tmux does. But tmux lets you have multiple windows open at the same time. So you might have noticed by now that I can have like multiple panes open during the lecture to code in different ways. The way you would do this in tmux is you press a key binding. If you download it fresh, it'll be Control-B and then %. So Control-B, %, and that would actually split your screen vertically. Control-B and then double quote to split it horizontally. And then I don't know what the key binding is. By default, I've reconfigured mine, but you can actually go between windows in tmux as well. And this gives you a nice development workflow where you can like write some code on the left, test.c, and then on the right here, oh, well, I can't apparently. But what I was trying to show is you can go back to the right-hand side and keep coding. I don't know, just not essential, just something useful to know is how you can use these terminal multiplexers to like better develop code so you're not like quitting and compiling, quitting and compiling. You can do things faster. All right, any questions before I go over I guess this is the recap of these 2 lectures. Back-to-back lecture, yeah?
Those windows count as separate processes, right?
In tmux, I don't think they do. We can actually check. So, there we go. Actually, it seems like they are. You can see they have different bash shells. So there are different shells attached to each of these windows because the PIDs are different. So they are different, yeah. Okay, so I know that was kind of a lot. Again, we have to pack some lectures together. This is one of those days where we pack 2 lectures into one. But the main takeaways are just what processes are, what they're useful for, allowing us to run multiple programs at once with this idea of time sharing. That's kind of the big takeaway for processes. How we can use standard output. So this lets us redirect the inputs and outputs of programs to files, reading or input from other files, and how we can connect processes together with pipes. This is all achievable because of this separation from standard I/O from programs implementations. So yeah, example of pipes. I'd recommend practice writing a few pipes. Like it can be kind of fun. Look up some Linux commands that you can use. You can combine with pipes. Just get some ideas. There's like one command that's kind of nice is sort. It lets you sort some output. So I don't have an example on here, but like just look up Linux commands that would be fun to connect with pipes. Just find a way to practice. Find a way to practice with these commands. You can just type the ones that we have on the course website because I will be asking you probably some commands related to pipes, some questions related to pipes on the exam. So keep that in mind. And then of course process control, how we saw how we could start a process, resume a process, all the different ways of doing that, how we can actually manually send signals. Just keep those things in mind. And that's it. So if you have any questions, you can ask me during office hours or right now. And if not, I'll see you all on Wednesday.